the impacts of global warming on people are going to be more than just the average change in the temperature. In that it's like a fever. So if you have a fever of 104, what you feel is a lot more than just a couple of extra degrees of warmth. What you feel is your head hurts and your stomach hurts and you're sick, and it's more than just the temperature. On the Earth, the strongest climate impacts are likely to be regional impacts rather than a globally averaged sort of a change. So it's kind of like if you have a log that's on fire and you increase the amount of oxygen, you can kind of predict overall that the log will burn faster in some way. But what you really want, what's actually affecting a little bug crawling on the log or something like that, is the flickering of the flames and how that might sort of change. And that's a lot harder to forecast. So I have my students read this book by Mark Linus called 6 Degrees, Our Future on a Warmer Planet. And he divides, the book is divided into chapters that correspond to different amounts of warming. And he's describing the various climate impacts that people have predicted, scientists have predicted, as a function of the amount of warming where those start to kick in. So if you're interested, I recommend you have a look at that. I think the most severe impacts are likely to have to do with water availability and drought and things like that. So it's a bit paradoxical. Overall, when you make the planet warmer, warmer air can hold more water vapor, and if you're sort of running the air through the ringer of the hydrological cycle of having it go up and make clouds and come back down and all of that, you get an increase in the overall amount of rainfall as the Earth warms. But as it turns out, places that are dry today are predicted to get even drier in a global warming sort of a world. So a continental interior sort of dries out as the temperatures go up. And so in continental interiors, there is expected to be a deficit of rainfall relative to the pre-warming sort of a case. So here is a plot of a map of where the rainfall changes are expected to be found as a composite from all of the different climate models that are used in the IPCC scientific assessment. And it's hard to predict regional climate changes, which means that different models don't always agree exactly on what they expect to have happen here or there. But there is some coherence that's coming out from the models. What you see is drying in places where it's actually anomalously dry today. So the American Southwest, the Mediterranean, Australia, these are all places that are drier than they should be today, and they are predicted to get even drier in a warmer world. Monsoons are a pattern of rainfall that seems to be particularly sensitive to global change because they are driven by the temperature contrast between water and land. And so large-scale changes in the climate can change these temperature contrasts and really change the patterns of rainfall that are to be expected, more so than the sort of normal storm kind of rainfall that you get in other parts of the world. So the American Southwest is not actually considered a monsoonal system, but the rainfall there is very heavily impacted by the temperature contrast between the land in the desert and the water temperature in the Pacific or the Gulf. The American Southwest is in drought today, and we know from proxy data from the medieval time that there were droughts in the American Southwest that were vastly larger than anything we have experienced. So the Dust Bowl was a picnic compared to the droughts that clobbered the classic Mayan civilization, for example. The African Sahel is expected, according to the Linus book, to be impacted at about 1 degree C of temperature change, and it's supposed to get wetter, according to the climate simulations. The China highlands are supposed to get drier at about 2 degrees of global warming. The Asian monsoon is supposed to get stronger and stormier under that 2 degrees C of warming. So every place is sort of cutting a different deal with, global warming. It's not all the same impact. It varies from place to place. Vegetation can have a strong impact on water scarcity, because when you have vegetation, it tends to mine groundwater and drive it to evaporate and then recycle to perpetuate rainfall. And then when the vegetation is gone, the rainfall just runs off instead of re-evaporating. And so vegetation can sort of provide a kind of tipping point where things can hang on under water stress, and then all of a sudden the vegetation dies, and then it takes more water even to get back out of the drought than you had originally. So some examples of rainforests that are vulnerable include Queensland, Australia. The high altitude rainforest is expected to get sort of chased off the surface of the earth as the climate zones warm, because you can't go any higher up in the mountains to get to a cooler climate. And so that's vulnerable under fairly modest amounts of warming. The big rainforests, the Amazon and Indonesia, are in the 3-degree chapter in Linus's book. It's very speculative and model dependent whether these rainforests could actually collapse or not, but it's certainly a possibility. We know that because the Sahara used to be a rainforest during a time in the early interglacial time called the African humid period, about 8,000 years ago. And it abruptly stopped, collapsed, as diagnosed from pollen records in sediment cores off of Africa. Nebraska used to be sand dunes. It looked like the Sahara. It's a place now called the Sand Hills. And these date from medieval time, when it was so dry in the other parts of the American West. So these things are definitely open to change. It's one scary possibility is that the end game for some jungle like the Amazon would probably involve fire. So if the conditions are just wrong and the plants are not thriving and everything dries out, you could have big fires that could suddenly release CO2 to the atmosphere, as well as carbon monoxide and soot and things like that, sort of announcing and punctuating the demise of such a rainforest. So there are two ways that the rise in sea level can affect people on the ground. One is in low-lying areas where you have the surface is very close to sea level. There's a gradient in the water in the soil between fresh water that comes from rainfall that can be used to feed the crops versus salty water that's sort of encroaching from the ocean. And if you raise the sea level and you bring the salty water too close to the surface, you can poison the agriculture. So there are islands in the Pacific, low-lying islands that are making plans to evacuate in the coming years because their agriculture is no longer possible because of salt encroachment. But a more dramatic impact of sea level rise comes during storms, which tend to pull the sea level up. It's called a storm surge. It's like a really high tide that sort of follows a hurricane. And so Hurricane Sandy, for example, in New York, had sea level higher than it would have been if the sea level hadn't been rising over the last few decades. And what's important is when the sea level crosses some critical height where suddenly it can spill over a levee or flood the subways or something like that. So the rise in the background sea level coupled with storms that seem to be increasing in their severity, which we'll talk about next, can sort of multiply each other to exacerbate this impact of rising sea level. So the big behemoths in the sea level picture are the two ice sheets in Antarctica and in Greenland. So here's something of a cross-section of the Antarctic ice sheet. Here's the East Antarctic ice sheet, the Transantarctic Mountains, and the West Antarctic ice sheet. So one thing that you can see is that the land where the ice is sitting on is actually lower than sea level throughout much of the western part of the ice sheet. So you may wonder how you could do such a thing like that. How do you stick ice onto a piece of land that's underneath a whole bunch of water? Well, it turns out that the land was above the surface of the water when it formed, but this process of isostatic adjustment, the weight of the ice gradually over millions of years pushed the land down. And so now the ice is extending down below sea level. It's grounded below the ocean. So this leads to the possibility that if it starts to melt back a little bit, the grounding line gets deeper and deeper as you melt it back, and so that makes it easier and easier for the ice to float up off of the ground. And once it floats up, it can flow in one of these things, which is called an ice shelf. So ice shelves can be hundreds of meters thick. They're not like sea ice, which is just a few meters thick. They're like giant cliffs of ice that you can see, and they are actually floating in the water. So an ice shelf itself, when it melts, doesn't cause the sea level to rise because it was floating already. But the ice shelf can act to sort of pen in the outward flow of ice from the ice sheet itself. And so when these ice shelves crumble and collapse, as we have seen them doing in the last few years, they can allow the ice behind it to flow more quickly into the ocean. The Greenland ice sheet, in contrast, is not grounded below sea level, but it is extra vulnerable because it's warmer at the surface. In Antarctica, the surface of the ice is always pretty much below freezing. And so the only way to melt the Antarctic ice sheet is to flow it off into the water and melt it in the water, maybe let it drift away up into warmer climates.